why I keep forgetting. Yeah, the same reason why I forgot to, stop the class in time is the same reason why I forget to start the recording, because I'm too into the derivation, I think. Yeah, right. So going by the same analogy, all right, we can say that your this will be nothing but expectation value of BA. Now, please remember, expectation of value of BA is not the same as the expectation value of AB. Why? Because AB need not be the same as BA, right? And then you have over here, you will have expectation value of B, expectation value of A, but it doesn't matter the order over here, simply because these are numbers and you can happily commute them, right? So now what do we get? Let's work out this particular step over here. You have FG minus GF. So what will you get now? You will get expectation value of AB minus expectation value of AB, okay, minus, what do you have over here? BA minus, now I'm going to shift these values over around and I will write it again as AB. Because remember, again, they are numbers and we know numbers commute. Just a second, I have to admit a few more people. All right, done. Okay, now what does this give me then? It gives me AB minus BA, right? Because the other factor cancels out. So this can be written as expectation value of AB minus BA, right? Which can be written as expectation value of commutator of A, comma, I've been hammering all of you about the comma, B. Okay, so I wrote it with a nice long tail, right? Okay. So everybody with me? Is this okay? Are the steps clear?
Yes, ma'am.
Okay, fine. So let me go to another page now. And this page is here as well. So now what do we have? We essentially have to prove our thing. So if you remember, your sigma A square, sigma B square was greater than or equal to, I'm going to just write it down now. Okay. What was it? Modulus of 1 by 2i. Okay. What did we have over here? Fg minus Gf, correct? Whole square, not whole square, sorry. This would be mod square, correct? So now what do we get over here? So it's greater than or equal to, let's write it down, modulus of 1 by 2i. What did we have over here? Expectation value of commutator of A comma B. Yes, everybody with me? So now what do we have? Let's take square roots on both sides. And what will we get? We'll get sigma A, sigma B is greater than or equal to 1 by 2i expectation value of commutator of A, B. Okay? This what we have derived over here is your generalized uncertainty principle. Okay, this is your generalized uncertainty principle. What we can do now is to try and derive it for your position and momentum. Okay, so let's give it a shot. Now, what I really want you to remember, okay, I mean, I'm sure Meera ma'am has talked about this. If she has already talked about the uncertainty principle, if she hasn't, then she will discuss it. But nonetheless, I'm going to go ahead a little ahead and talk to you. Remember that you have three components of your position, right? You have x, you have y, and you have z. Okay. Remember, what you cannot simultaneously determine along with x is px. That is the component of the linear momentum in the x direction. Okay. So these are what cannot be simultaneously determined. Okay. Similarly, you cannot determine y and py together or z and pz. But if you ask me whether I can find out x and pz together, there is no problem. Okay. Please remember. All right. So this is something very important you have to remember. Position and the component of the momentum along that direction, okay, is what cannot be determined simultaneously and precisely together. So let us try and now get the momentum position, what do you call it, the way you know it. How do you know it? Delta x, delta px, okay, is greater than or equal to some h cross by 2. That's what you write, right? So let's get it from the generalized um, uncertainty principle. And how do we do that? So essentially, it's like this. Your sigma of x, sigma of px must be greater than or equal to 1 by 2i expectation value of commutator between x and px, right? So I'm hoping you've already done this with Meera ma'am, in which case you will know that this is nothing but I h cross. It's of course a number, so it will just come out. So it is greater than or equal to 1 by 2i into I h cross. Your I and I will cancel. So you will get sigma x, sigma px is greater than or equal to h cross by 2. Okay, this is the way you know it. Uncertainty, or if you want to write it in the other term, you will get delta x, delta px is greater than or equal to h cross by 2. This is a familiar thing that you know perhaps from your BSc. But this is the way we write the generalized uncertainty principle. Okay. Is this clear? Has everybody got this derivation? Any doubts, please?
No, ma'am.
Okay. So now before I go on, okay, I'm going to say something a little, interesting. All right. So before I go on, see, is my pace okay? I know I'm going slow, but is it okay? Is everybody understanding things? I'm going to stop the share right now. Okay. And I'm just going to ask everybody, is it all right? Is everybody following, or is it too slow? I cannot make it slower than this, but I can certainly make it faster. So I want to know from you whether it is too slow, what I'm doing so far.
Ma'am, this is perfect, ma'am.
You like it this way, right?
Yeah, yes, ma'am.
Everybody agrees with that? Is it okay?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So now what I want to tell you is that they say formalism 13 hours, okay? At the pace I am going, I will not be able to do it in 13 hours. This is my experience from the time I have been teaching formalism, that it takes me 18 to 19 classes to do it. Now, since we have it online, I cannot see who is absent when and take their class, which is what I have been doing all these years. Okay. I see who has finished first, who is absent when, and I go and take off their classes. Okay. So right now I'm not able to do it. Okay. Because it's online. So which is why on these, I think there are certain days in which your 4 to 5 class is free. Okay. So which is why I tried to book the class tomorrow and the one on 5th of May. And I hope that is not a problem. Okay. The reason why I'm doing it is I know it has to go at this pace. Okay. Because otherwise I am a little scared that I will say what I have to say and go away, but you will not follow. Okay. And I don't want that. Okay. I want everybody to follow. Everybody. Okay. Not just, there are some people who are way, way smarter than, in my class also in an MSc. I still have people who are way, way smarter. They understood everything the teacher said when the teacher said it once. And they said, yeah, yeah, we've understood. Let's move on. Okay. But then people who didn't follow things at that pace got left behind. And I don't want anybody to get left behind. Okay. This is my policy. It's just that, sometimes you may need a little more time to just absorb the whole thing. Okay. Everybody is not the same, right? So if it is okay with it, please don't be upset that I'm taking your one free slot in the week, the 4 to 5 hour, and please, let me take the class tomorrow. Once I have enough covered enough and all, I will not bother you with extra classes. Okay. So tomorrow and on 5th of May, I will take that extra class. Okay. So just wanted to clarify because some of you may be a little angry with me for taking it. Okay. Now, what I wanted to tell you, let me just go back and share the iScribe again. Okay. All right. So how do we understand uncertainty in terms of a measurement? Okay. So the way I wanted you to understand is that, so I will just change the page. Okay. And the way we see it is that, you basically do it like this. So let us say we are measuring position. Okay. So you are measuring X. All right. And on this side, you will have the number of times you have measured a particular value of X. Okay. And usually what you will find that even if you're supposed to get one value, what you will suppose you're supposed to get this value. This is what we call as the expectation of X. Okay. You will find that you will get essentially a Gaussian distribution. Okay. So it will go, it will peak at that value, then it will come down again. Okay. This is how it works. What in this is your sigma X or your delta X? What is this? So what you do is that you take, this is your maxima, you will take half of that, and then you will have this position where it cuts and this position where you cut. So you go down here, okay, and this difference, okay, is your delta X. Okay, so that is your full width at half maximum. So full width at half maximum. Okay, and what did I tell you this distribution was? It's a Gaussian distribution. Okay, now what I want you to remember is that X and Px, okay, they are essentially related through a Fourier transform. Okay, just like energy, okay, and time. So usually you will say it as frequency domain and time domain. Okay, they are also linked through a Fourier transform. Now, why am I saying this? Okay, you want X, all right, you want X, you also want Px, correct? Now, Px also there will be something similar, right? It will be something similar. So you will have Px values here, right? And you will have an expectation value of Px, correct? And this is, of course, the number of times you're measuring a particular Px, all right? So this is the expectation value where the number of times you're going to measure it is going to be the highest. And then again, you will have a Fourier distribution, a Gaussian distribution, sorry, Gaussian distribution. Now remember that this and this are connected through a Fourier transform. Now what you can ask is the question is that when I transform a Gaussian function, a Fourier transform of a Gaussian function, what is it? Okay, so what you have to understand is that if you have a Gaussian function and you do a Fourier transform, so now I'm going to call it a FT, means Fourier transform, okay? You still get a Gaussian function. And that makes sense, right? Because here you're getting X, here you're getting your Px. But there is one difference. So the way Griffiths puts it, and you will, I think, understand it and remember it, because I remember it best like that, is that a fat Gaussian, the Fourier transform, will be a thin Gaussian. And similarly, if you start off with the thin Gaussian, you will go back to a fat Gaussian. So what does that mean? It means that if you have, okay, so this is your x, and this is your nx, this is your expectation value of x. If you have a thin Gaussian, what does a thin Gaussian mean? It means that your FWHM is low, or your delta x is low, which means your uncertainty is low, correct? If you take a Fourier transform of that, it's a thin Gaussian, it will go to a fat Gaussian. And what will happen? So that will be the case. This is your px, this is your number of px, and you will get something like that. Okay, this is your delta p, your expectation value of px, and here you can see this is your full width at half maxima. It is very small. Here this is your maximum, this is your half your maximum, and here you see your delta px has become very, very large. Okay, so this is basically the way to remember it. The relation between quantities that are linked through a Fourier transform, you will definitely have the uncertainty principle, because they are Fourier transforms of each other. And if one has a Gaussian distribution with the full width of maxima at half maxima, which is small, when you do a Fourier transform, the thin Gaussian becomes a fat Gaussian. And when it becomes a fat Gaussian, obviously, you're going to get a much larger uncertainty. Okay? So there is no way you will be able to precisely measure both of them. If you take the ultimate case that you know precisely what that x is, what does it mean? It means that you have shrunk the Gaussian to become a line. Your delta x has become 0. That is a very, very thin Gaussian. You go take a Fourier transform and you get the fattest possible Gaussian, which means you're completely uncertain about the momentum value. And the same relation holds good about energy and time. Okay, this is just a little bit of extra material so that you kind of appreciate what is going on. All right. Okay, so with this, we will stop about the uncertainty principle. What we will do now is we will go on to something which I have been harping on all along. Okay, let's understand why I have been going a little crazy about it. And this is about unitary transformations. Okay, now unitary transformations, you have of course come across this term before, unitary. Unitary transformations obviously are going to involve unitary operators. Okay, so let us first of all figure out what are unitary transformations, and secondly we'll try and figure out why are they important for us. So let me just arrange my notes a bit, then we will get started. Okay, so let me again change my page and change my page here. So, all right, somebody has come in now. Delete the person. Right, so now let us ask ourselves, what do I mean by unitary transformations? So let me write it down, unitary transformations. So where did I mention this before? I mentioned it once when we talked about unitary operators. I said unitary operators are very important because they are going to be used in unitary transformations. The other thing that I mentioned unitary transformations for was when we were trying to prove that if two operators or observables commuted, then they had a common set of eigenfunctions. If you remember, this problem came out when the eigenvalue was degenerate, right? And then we got a representation for one of the operators, a square matrix representation. And then I said we need to diagonalize it, right? And for that diagonalization, you need a unitary transformation. And I said, don't worry, unitary transformations will not change the physics of the problem. Okay. So this is where we are going to start looking at that in a little bit of detail as to whether unitary transformations actually maintain the physics of the problem. Okay. So let me talk about that. So we are going to talk about now unitary transformations. So first of all, what is a unitary transformation? So let us imagine that you have a vector space. Okay, so this is a vector space. Obviously, this is something that is describing all possible dynamical states of some physical system. Okay, so this is a vector space. Let us pick out two wave functions from here. Okay, so we will pick out a wave function psi, and let's pick out a wave function, let us say x. Okay, and what is the relation between a and x? So these are wave functions. And of course, you know, wave functions have information, but they are by themselves, okay? We are very happy they have the information, but we need operators, right? To understand, to read that information. So you need an operator, and let us say A is an operator. And the relation between this X and this psi is that your A operating on psi yields this wave function X. Okay, let us imagine this is the relation. Now let's start talking about unitary transformations. So what are unitary transformations? So you will take a unitary operator. Okay, let us call it U. And then what do? You operate U on every wave function belonging to this vector space. You operate it on every wave function belonging to this vector space. Okay. And of course, you will create now a new vector space. What I'm trying to tell you is that when you do something like this, you do not change the physics of the situation at all. What do I mean by that? It basically, what I'm trying to tell you is that, look, how do I know I have not changed the physics? I will only know I have not changed the physics by making measurements on the new system, right? Yeah. So I had this vector space. Now I have put this unitary transformation. I'm operating all the wave functions belonging to this vector space with this U, creating some new wave functions, and I'm creating a new vector space, okay, which I'm calling F prime. All right. What I'm trying to tell you is that the physics has not changed in F prime. How do I know? The only way I will know is that when I make measurements, I should get the same answers, correct? So which means what? Eigenvalues should not change. Okay? Eigenvalues should not change. That is one thing that is required. Next, we may not always get eigenvalues, right? Then we can say that expectation values should not change. Okay? What else can we think of? Can anybody tell me something else that should not change? we can say commutator relations should not change. So commutator relations should not change. Right? Then, for instance, one thing we could say is that, the formulae, okay? So with which I associate one quantity with another. So for instance, we all know that in a gravitational potential energy is mgh, right? Now it should be that, even if the system has been transformed and the physics has not changed, I should still have a formula which says potential energy is mgh, right? It should not change. So how do I say it in quantum mechanics? I will say operator relations should not change. Okay. Right now I cannot think of anything else. If you can think of something else, please tell me. But if all this is not changing, then I'll say the physics has not changed. Okay. Now you can ask the question that, ma'am, if the physics is not changing, why should I bother with these unitary transformations? I mean, why go through all this hangama and do all this thing called a unitary transformation if the physics is not changing? Well, the answer is this. Sometimes, it may be easier to solve a problem in f prime than it is in f. And I'll give you an example. You are some working in Cartesian coordinates, okay? But suppose now something is there which is a spherically symmetric problem. It makes sense for you to go from Cartesian coordinates to spherically polar coordinates because the symmetry of the problem is such that it's easier to solve it in spherical polar coordinates. Sometimes it may be easier to solve it in cylindrical coordinates. Of course, you can solve it in Cartesian coordinates. Who said you can't? But the problem becomes very tough. But that same problem can become easier if you just do a change in the coordinates. When you're doing the change in the coordinates, the physics of the problem is not changing. And what you're doing here is exactly that. You are changing the way the system appears to look, but you're not changing the physics. But now, my basic thing is that I have to show you that the physics is not changing. Okay, you should not buy what I'm telling you, right? You should reason it out, isn't it? So let's try doing that. So, what do we know about the unitary operator? We know if U is a unitary operator, then U dagger. What is U dagger? It's the adjoint of U. If U is a matrix, then we would basically change the rows to columns and replace every element with its complex conjugate, and we would end up with U adjoint. U dagger must be equal to identity is equal to U dagger U. This is all we know. And after this, I have to prove all these claims that none of these things are actually changing. Why is commutator relations important, please? See, for the physics to remain the same, you cannot say that, look, I cannot measure position and momentum simultaneously in that first vector space. But then I do a unitary transformation, and now I can measure position and momentum simultaneously. Imagine how ridiculous that would be, okay? So commutator relations should be maintained the same, okay? They are very, very, very important. Right. So before we do this, okay, so let us now, first of all, write down. We have psi in the original, x in the original. These are the wave functions. And then we will do a u psi, which gives us a psi prime. And we do a ux, which gives us a x prime. Right? Now here, so these are, as I said, wave functions. Correct? And these are the wave functions. They are the new ones. Here I have A, which is an operator. The first thing which I need to know is how is this operator going to transform? All right. What do we need? Over here we know that in the old system, your x is equal to A psi. Here we need that your x prime will be equal to some new A prime psi prime, right? So what question is, what is the relation between A prime and A? That's the first thing we need to find out. Okay, after that we can try proving all these things. Okay, so any doubts so far? Has anybody any doubts? We can clarify and then we can move on. Are you all good? Yes? All asleep after lunch.
No, ma'am.
Good. Thank you, Monica. That was very nice of you. Yeah, see, at least Monica is awake. I'm happy about that. Okay, so let's move on. Yes, Tejashri, you have a question. Please ask. Tejashri, I can see that you have raised.
Excuse,
Yeah, please.
ma'am, you said eigenvalues should not change, right, ma'am? Excuse me, ma'am.
Yes, yes, I'm here listening to you. I said that eigenvalue should not.
What about eigenfunctions?
Yeah, you will see that the eigenfunctions are nothing but unitary transforms of the old eigenfunctions.
Okay, ma'am.
Eigenvalues will not change. Why should eigenvalues not change? Because what you are measuring cannot change. Right? I cannot measure one value of position, and just because I did some mathematics in the background, I should not get a new position, right? Because the physics should not change. Okay?
Yes,
Whatever
ma'am.
I do with the mathematics, it doesn't matter. That's what I meant. Any other doubts, please? Thank you for asking, Tejashwi.
Yes, ma'am.
Any other doubts, please? If they aren't, let's progress. Okay. So, yeah, I shouldn't forget to change my. So, what I'm doing now is I'm going to save all my class, whatever I'm writing on the, the blank sheets. All right. I'm going to save them and I'm going to put them up also in the drive. All right. Along with the lectures. So I'm hoping that you will all be able to see it. Now, please make sure that you make your own notes, because at some point my drive is going to get clogged and I have to start deleting the old lectures. All right. So please, yeah, keep making your notes or looking at them as and how. Don't keep it for the last instant. Okay. I will talk to you people before I delete things. So don't worry about that. Okay. So now again, let me just repeat. You have x and psi. Here you have x prime, which is equal to ux. You have psi prime is equal to u psi. Please remember, these are all wave functions. You have an operator a, and x is equal to a psi. Here your equivalent is an operator a prime, and we know that x prime should be equal to a prime psi prime. And what I asked was the question that is, or rather, let me cut this off. What is the relation between A and A prime? Okay, this is the question that I'm asking. All right. I heard something. Does anybody else have a doubt? Tejashri, I can still see a raised hand. Maybe you can remove it. Okay. Otherwise, if you have another doubt, ask me.
It was previous one.
Okay, fine. Right. So now let's go from this relation itself. Okay. Yeah, this relation itself. So your x prime is equal to a prime psi prime. But what is your x prime? It is nothing but ux. Correct. And this is equal to a prime u psi. Correct. Further, we know that x is equal to a psi. So I will write it a u a psi is equal to a prime u psi. So now let's do one thing. Let us operate on both. So we can say then this implies that ua is equal to a prime u. Okay, so this is what I'm writing, because it will be true of all wave functions. Okay, so we can write this. Now, operate on both sides from the right, okay, with U dagger. Okay, so this is what we are going to do. So therefore we will get UA now operating from the right with U dagger is equal to A prime U dagger. But we know something about U dagger, right? It is nothing but the identity. Why? Because U is unitary. So we will get now over here A prime I, which is equal to A prime. So therefore, A prime is equal to U dagger. Please remember this. Okay. So wave functions, how will they change? So if you have a wave function psi, it will go to U psi. Operators, how they change? If there is A, it will go to U dagger in a unitary transformation. Okay. Is this clear to everyone? Is this clear to everyone? How this is happening?
Yes, ma'am.
Yes, ma'am.
Okay, cool. So now let us start off proving things for ourselves, trying to say that if this is happening, if we are doing the transformation with these rules, okay, then the physics does not change. So first thing we will prove is that if A is Hermitian, then A prime is also Hermitian. Okay. Why is this important? Please tell me. Because we know if A is associated with a dynamical variable, a real physical dynamical variable. For instance, A is linked with position. Then I know that eigenvalues of A are real, so I can make sense of that measurement. Correct? Now, once I do the unitary transformation, suppose it becomes a non-Hermitian operator. Sometimes when I'm trying to make measure positions there, I will start getting imaginary values and I cannot make sense of it. So it is very important that if A is Hermitian, after a unitary transformation also it should remain Hermitian. Okay, so what do I need to prove? So I'm going to write to prove that A prime is Hermitian implies that we have to prove that A prime is equal to A prime dagger, right? Yeah, I need to be able to prove this. So let's try doing this. So we will say that you know that A prime is equal to U dagger. This implies that A prime dagger is equal to U dagger whole dagger, right? So let us now see how we can do it. We can do it like this. We can say it is equal to, you remember, let me just write it here. Okay, AB dagger is equal to B dagger, A dagger. Somebody had even asked me a question. So we are going to use this property. Okay, so let us now take UA to be sum together and we'll take the U dagger separately. So I will write this as U dagger dagger. Okay, and here I will have UA dagger. Okay, then this will be equal to U dagger dagger. What was that? The property was A dagger dagger is equal to A. Okay, so remember these are the properties I've already given you of adjoint. Okay, so this will be now U dagger dagger will become U, and this over here again we will apply the same property. Okay, and we will get A dagger U dagger. But what do we know about A dagger? A dagger, A is Hermitian, correct? If A is Hermitian, it means that A is equal to A dagger. So thereby we can write it as U dagger. But what is UA U dagger? It is nothing but A prime. So therefore, A prime dagger is equal to A prime implies A prime is Hermitian. Okay? So this is the first thing that we see, that if an operator is Hermitian, after a unitary transformation also, it remains Hermitian. And that is extremely important. So let me see what time it is. I don't want to overshoot my time again. Okay. Let's go for the next property. And this next property essentially tells you that operator relations do not change. Okay. So as I told you, you have in one case, say your kinetic energy is mv square by 2 or half mv square. You should not have a unitary transformation and then have your operator have some other formula. That doesn't work, right? So let us see how we can write this down. So this is the next thing. So I will stop after this. So operator relations.
Ma'am,
Next
next
page,
page.
ma'am.
Next page, ma'am.
For thank you. I'm sorry, I've sat and scrawled on it. Okay. So let me write it again. So essentially, operator relations do not change. Okay. Now, how do we write this? For instance, so we are just going to guess some formula. Okay. So suppose you have now some operator A, and this is equal to some scalar constant C1 times operator B plus some scalar constant C2 times operator C and D. Okay. So please remember A, B, C, D. These are all operators. Okay. And what about C1 and C2? These are scalar quantities. Okay. All right. These are just scalar quantities. They are not operators. All right. So now, what do we need to prove? We need to prove that once everything has been transformed, your A prime is equal to C1 B prime plus C2 C prime D prime, where A prime is equal to UA U dagger. B prime must be equal to UB U dagger. C prime must be equal to UC U dagger, right? And D prime must be equal to UD U dagger. Okay, so you need to prove this. So how do we prove this? Okay, how do we prove this? Let's start off with this itself. A is equal to C1B plus C2 CD. Let's do a transform on A. So you say UA U dagger will be equal to what? I'll have to do this for this relation also, right? Correct? Because A is equal to C1B plus C2 CD. Now let's do this. So this means I have U C1B U dagger plus U, plus C2 CD U dagger. Okay, go further. This is a scalar constant, so this will come out. You will get U B U dagger plus, I'll put out C and I will get U C D U dagger. Let's come on to this side. UA U dagger is nothing but A prime, which is equal to C1. UB U dagger is nothing but B prime plus C2 Now here you have U, C. Now in between this CD, I'm going to put in a U dagger U. D, U dagger. How can I put in a U dagger U? U is unitary. So U dagger U is nothing but an identity. So I can put in an identity, right? It won't change it. So now what can I write it as? C1 B prime plus C2. Now I'm going to group these things. Okay, this last term, I will write it as UC U dagger, and I'll have U D U dagger. So then I will get C1 B prime plus C2 C prime D prime. Okay. So on this side, of course, I have my A prime, and thereby I have proved it. Hence proved. This is what I wanted to prove, right? Okay. And this is the same. So I have proved it. I have proved that operator relations do not change. So we will meet tomorrow again, and I will start off with telling you how in unitary transformations, commutator relations, eigenvalues, expectation values will not change. Okay. So are there any doubts? I will stop the share right now. Excuse me. Stop the share, and I will ask you again, are there any doubts? People mostly
ma'am.
understood?
No, ma'am.
Okay,
No, ma'am.
good. But look over all these things that I've told you today, both the generalized, you know, uh, uncertainty principle, as well as what I told you so far about unitary transformations. If you have any doubts tomorrow, before we start on anything new, we will get them cleared, and then we will move on. Otherwise, we will see each other tomorrow at what time? 4 o'clock. Okay. I will send you a meeting notice early enough.
Thank you, ma'am.
Okay, then.
Thank you,
Yeah.
ma'am.
Have a nice evening, everybody. I know you have one more class left. It's a bit tiring, I know, but at least you're at home, I guess. I'm hoping so. And stay safe, everybody. Okay. So, fine. I will finish, wait for everybody to finish.